So, welcome everyone to the second day of IEEE Online Forum on Climate Change Technologies. Today we have our first speaker, Ayman El-Refaie, who is a fellow of IEEE and the president of IEEE Industry Applications Society. Today he'll be talking about energy conversion for a sustainable future, revived role of power and energy. With this, I would like Ayman to start his presentation after a short introduction of himself. Ayman, you have roughly 40 minutes for this presentation, followed by question and answer. Over to you, Ayman.
Okay, thank you. Thank you very much. And good morning, good afternoon, good evening, everyone. And I'm very happy to join this event. And thank you, Charlie, for inviting me. Just a brief background about myself. I am Egyptian originally. I came to the US about 26 years ago to do my PhD. I did my PhD in electrical machines at University of Wisconsin-Madison. After that, I had a career in industry for about 12 years. I worked for General Electric at their Global Research Center, and since 2017, I have been a professor at Marquette University in Milwaukee, Wisconsin. And since time is short, I kind of have probably more slides than the 40 minutes, but I'll be judicious in what I cover. The presentation today, the goal is to kind of give you a high level overview of what's happening in the energy conversion space to achieve a sustainable future. So we are going to cover various applications, but again, at a high level, I know that probably the background of the attendees is very diverse. At the beginning, obviously, I want to thank the colleagues at the Industry Application Society, my ex-colleagues at GE, and also my research team at Marquette University. So this is kind of the outline. I'm just going to go through a brief introduction and then a definition of electrification, and then go through several examples of what people are trying to do to achieve a sustainable future, and talk about some new trends and areas of research and conclusions. So in terms of talking about energy sustainability and electrification and all of this, I mean, it's easy to get lost in the middle of all what's taking place, especially globally. So I choose to start by kind of clustering, at least from my point of view, few mega trends that have been really pushing a lot of activities in terms of R&D towards more electrification and a more sustainable future. So the first one of those mega trends is e-mobility or transportation electrification. So this is moving towards more electric transportation. Maybe the space that many of us are familiar with and is commercially available today is the automotive space, the light duty vehicles. I mean, today there is a wide variety of hybrid and electric vehicles that one can buy if he chooses, or he or she chooses to. But that space is much broader than that. I mean, there is big efforts for electrifying mass transit, mining applications, as we'll talk about a little bit, aerospace over the past 10-15 years. There is a lot of effort for electrifying the propulsion of aerospace as well as marine propulsion. The second mega trend is renewables. And basically, we see globally that we are changing the mix of power production. So instead of just relying on the conventional coal and natural gas power plants, today globally, wind and solar specifically are becoming key players in our mix of power production. And also there are other areas or technologies that are coming in the pipeline, geothermal, tidal, and wave, that are still not as mature. But again, a lot of work has been done in that direction. The third mega trend is dealing with harsh environments. So in general, even in the oil and gas industry, we have been moving production to remote locations and harsher climates. So, for example, we subsea oil exploration, sour and acid gas compression, downhole and geothermal pumps, underground mining. We'll talk about several of those. So in general, to be able to produce a lot of types of energy, you have to deal with harsher environments. At the system level, and that this is kind of, I don't know about various countries, but especially in the US, we are dealing with a relatively constrained electricity grid. So basically, we have been dealing with increasing demands on a constrained infrastructure, and there has been a lot of effort to figure out how to deal with that, as well as accommodate distributed power generation as we introduce more renewables, and also how to deal with the intermittency of these renewables. So again, this is my attempt of coming up with like 4 mega trends or so, just to kind of know what we are dealing with. In terms of like the technical scope, since I also I'm representing IES here in this presentation, the Industry Application Society is really kind of unique in its structure. It has 4 technical departments and 20 technical committees, and as you see from the name of the departments, I mean, we have process industries department, industrial and commercial power systems, manufacturing systems, development and applications, and then the industrial power conversion system. So if you look at the industrial power conversion system department specifically, and I don't want to single it out, but there are 6 technical committees that deal with electrical machines, drives, power converters, devices, transportation systems, renewable energy. So again, the society is very broad, and basically we are involved in almost every aspect of energy sustainability that you can think of. Again, this is more of an eye chart, but I just want to emphasize our breadth in terms of the technologies that we deal with. So you can see that under the process industries department, we have committees covering cement, petroleum and chemical industry, pulp and paper, metal industry, mining, electrical safety. And then again, you go from there to, like, for example, industrial lighting and displays, industrial automation and control. And then under IPCSD, what I mentioned, you deal with electric machines, drives, etc. So again, we are unique from that perspective, that we are very broad in what we cover, which I have to be honest is a double-edged sword. It's an advantage, but also when you tell people we come from the Industry Application Society, people don't know exactly what we are doing. Some societies, their name explains itself. For example, if you say I'm from the Power and Energy or the Power Electronic Society, it's kind of easier to grasp. That's why a lot of our time go into kind of making people aware of our identity and our breadth. So yeah, so let's kind of shift gears towards the more technical stuff, you know. So when we talk about energy sustainability, electrification is a word that people come across frequently, you know. So what do we mean really by electrification? There are several definitions, and it depends on really on the context of the discussion, but they all lead to expanding the role of electrical systems. So one definition, which is very basic, and is that we are trying to replace mechanical and hydraulic systems with electrical systems. That's a fun, like, basic and general definition. Sometimes in the context of renewables, we refer to expanding the use and integration of renewable energy sources. And then there is a third definition that's more specialized, that we refer to electrification, that we are replacing fixed speed electrical drives with variable speed drives. I'll talk a little bit about this later. But again, you can think of electrification that we are trying to replace existing systems with more electrified systems. That's kind of the bottom line, you know. And you are going to hear, or if you, depending on what you follow, the term more electric is becoming industry trend. So the people have been talking about the more electric aircraft for 2-3 decades now. There is more electric ship, etc. You know, so what are examples of electrification? And kind of I'm gonna walk through a number of examples just to show you also the diversity of this topic, you know. So I'm sorry, this is a busy slide, but I kind of included the information if depending on if people are specialized in this area, they can find enough technical information in that slide. But again, people might get the impression that if we are talking about electrification and energy sustainability, that we are not going to necessarily talk about oil and gas industry, for example. That's not true. In the oil and gas industry, for example, they have a lot of compression lines. So kind of the baseline system, if you can see my cursor, you can see that connected to the grid is a low frequency power converter at 50-60 hertz. This typically drives a motor. Historically, this is if it's something called induction motor, and it's typically low speed up to 1800 RPM, and then you have a gearbox, and this gearbox drives the compressor. So this is kind of a legacy systems, compression systems that are complicated and also not very efficient, you know. So recently in this industry, you can see now in the new system that they transition to. Now they use advanced power converters that are high frequency, so they can go up to hundreds of hertz. The gearbox is eliminated, and that's usually a good thing because gearboxes in any application means that we are going to have a lot of maintenance. And now the motor can be a fully integrated or directly integrated with the compressor. But that means that the motors that are used are high-speed motors. So instead of 1800 RPM, you can go to 20,000 RPM or so. In general, I know many of you might not have background in electrical machines, but for a specific power, if the motor or generator is rotating at a high speed, that means that the torque is lower, and that means that the physical size of the machine is lower. So if you look at this figure, this is kind of showing the specific weight in pounds per kilowatt, and the x-axis is the speed. You can see that at lower speeds you are up here, while if you go to like 10 to 20,000 RPM motors, you get about 90% reduction in mass, and that's huge in terms of reducing the system footprint and having a more integrated systems, basically a motor compressor set, you know. As I mentioned, on top of that, there has been a lot of work done also on drivetrains to deal with subsea and sour and acid gas applications. You know, so in terms of sealing and encapsulation. So just wanted to let you know that don't forget about the oil and gas industry. There is a lot of electrification that happens in that industry as well, and I intentionally started with it to bring it to your attention. You know. If we talk about renewables, again, I also wanted to start with a kind of geothermal, and ESP in the title refers to electrical submersible pumps. And the concept of electrical submersible pumps is kind of there is synergy between geothermal and also some of the oil and gas applications. So the whole idea is that you have if we talk about geothermal, you have an injection well where you kind of pump cold water down to a certain depth. Depending on the temperature that you want to reach, and then there is a production well where you are extracting hot hot water, and in some cases a mixture of water and steam, basically. But the uniqueness of this application, this kind of tackles the harsh environment aspect that we kind of mentioned in the mega trends. You can see here that we have a motor pump system, and you can see here, I mean, it might not be clear from this schematic, but the aspect ratio of this system is usually very extreme. These systems have very small diameters and very long length, so the design of the motor section is usually unconventional. I mean, it usually have multiple rotors supported by multiple sets of bearings, and also depending on how deep you want to go and the temperatures you are dealing with, you are typically dealing with hundreds of degrees C environment, and that makes it very difficult in terms of designing this system, in terms of insulation system, that the insulation needs to survive at hundreds of degrees C, and also in terms of the control, you cannot have a position or speed sensor at this temperature, so probably you need to do some sort of sensorless control. So again, think about these electrical submersible pumps as also another example where a lot of research and development is happening in the direction of geothermal and oil and gas applications. Obviously, wind continues to be one of the leading with solar. These are the two leading renewable energies that we are dealing with. And if some of you have looked into the details of wind, it's a fascinating application from an overall engineering perspective. You know, always size is what the first time you see a wind turbine close, you are going to be probably surprised by how big they are. You know, I mean, you can see here this kind of figure, and this is also, these are small wind turbines. You can see relative to some of the landmarks like the Eiffel Tower, the Space Needle in Seattle, that even like a 1.5 megawatt wind turbine is sizable compared to these. And 1.5 megawatt wind turbine is considered small today. I mean, for offshore wind, you are probably talking about 3 to 5 megawatts. That's kind of a typical range today. And if you look at what we have to deal with in a wind turbine, the blades, what you are seeing here in this figure is a composite blade, and you can see that how big one blade is. Usually one person can probably walk inside this blade. So blades are typically made out of composite cores, and they are obviously designed for to last, and also to maximize the annual energy production of the wind turbine. So a lot of work till now go into the blades out of all the components of the wind turbine. In the nacelle here, you have to deal with the drivetrain components, the gearboxes, the generators, and so there is always need to reduce the size of this as much as possible to reduce cost. That's kind of ongoing effort. And then also the power electronics that help connect the electricity produced from the wind turbines to be connected back to the grid. So again, a single wind turbine is truly a multidisciplinary application, you know. I just want you to give you an idea of how challenging the size is, you know, because in these cartoonish figures, it's not easy to see that. What you are looking at here is an example of a GE wind generator prototype. This is only 1.3 megawatt, but it is spinning at 56 RPM. So as we mentioned before, if the speed is low, then that means the torque is very high. You are dealing with 240 kilonewton meters, which is very high. And you can see that the size of this generator, and this is kind of the rotating part or the rotor of the generator. So you can start having an idea how big are the components that need to be fit inside the nacelle. And for offshore, there is typically a gearbox, which helps. But if you look at something like offshore wind is usually direct drive, meaning you cannot put a gearbox again, because it would be very difficult to maintain a gearbox off land, you know. And in addition, the offshore wind turbines go up to 10 megawatt. Today, I think the largest offshore wind turbine is about 15 megawatts. So you can imagine that you can take this size and multiply it by almost a factor of 10. And that gives you an idea how challenging it is to fit everything in this nacelle that's typically up a very high tower in the wind turbine, you know. So again, lots of engineering and research challenges. There is also synergy between offshore wind and tidal and wave energy, even though I'm not going to dive into the nuts and bolts of tidal and wave energy, but also anything in the water is again direct drive. Things are rotating at very low speeds. So a big challenge still ongoing with tidal and wave energy converters is how to get them smaller and cost effective. So in terms of levelized cost of energy, if you look at some of the recent reports, yes, solar and wind are very competitive and favorable compared to fossil-based options. Tidal and wave are not there yet. Still work in progress, you know. We are going to switch gears a little bit and kind of talk about what is at a very high level, what is a smart grid and smart buildings, because also we hear about this in the context of the vision for a sustainable future, you know. So basically, what a smart building, this is again, you will see many cartoonish figures like this showing that vision, you know. So the the vision is that you are going to have solar PVs for electricity production. What you see here is a solar water heater collector that's to provide hot water. That you are going to have smart lighting, smart appliances that can be controlled, including air conditioning system, that you might have an EV or a plug-in hybrid that you also connect to the house. And then so what you see is that you have maybe you have some wind turbine nearby. uh, so effectively you have a small power system, and you are trying, and you have like some sort of an electric energy management center that at any instant of time during the day is trying to optimize the energy usage of this building, you know. So that's kind of in a nutshell what do people mean by smart buildings, you know. So it's really more of um, I mean, it has a lot of details, but at the end of the day, it boils to more of a control and optimization process, depending on your supply and loads at any instant of time during the day. So very interesting work is being done in that area, you know. Uh, uh, Again, in terms of this stuff is available today. One aspect of a smart home is you can have smart appliances, you can have smart lighting that you can basically schedule to work. For example, for the appliances, you can schedule them to work automatically at times of the day when the electricity, when the demand or the loads are at minimum and the electricity prices is the lowest. The lighting is available today. So many of these aspects of smart appliances, smart lighting, the solar PVs, all of this is available today. Again, you need some sort of just brains for the operation and energy optimization, you know. So just talking about how to integrate renewables, kind of how to make this vision happen, you know. So, for example, solar, there are all kinds of interesting ideas people have been working on, you know. So we always envision the conventional houses in North America with some solar panels on the roof. But if you look at some examples somewhere else. This is an example of a building in Bahrain, which is one of the Gulf countries. I think that it's a kind of a World Trade Center building, and you can see that it has like 3 wind turbines integrated with the building. In terms of solar, I'm not sure if the video is going to work, but and probably for the sake of time, I'm just going to explain what this is. This is if you Google it, I think if you type solar flower, you are going to find the video for this thing. So as you can see, this is when there is good levels of solar radiation, this things opens up and kind of forms the shape of a flower. And also it can track the direction of the solar radiation. And then when there is not, when during the night or when there isn't enough levels of solar radiation, basically this gets, it looks like this and gets stuck inside this container or box, you know. So again, many interesting ideas how to integrate renewables with these smart buildings, basically. Uh, if we so where does all of this go for us as a society? Basically, in the past, the typical model was that we have like a power station at a certain location, coal or natural gas, and then from there you have step up transformers to step up the voltage, and then you go through a transmission phase. And the reason why we step up the voltage, that to reduce the ohmic losses in the transmission lines. And then once we reach kind of get close to where we want to distribute the electricity, we have step down transformers and then a distribution network till we provide electricity for the customers in the different locations, you know. The new envisioned model is that we are going to have what is referred to as distributed generation. So you can see that we are going to have wind power, we are going to have solar panels, we might have some level of energy storage, batteries or something else to address the intermittency of the renewables. So again, it is a kind of a multi-port system, you know. And again, at a high level, similar to what we said about smart buildings, is applicable to smart grid as well. That at any instant of time, you are trying to optimize or match the loads to the best mix of energy production. So at any instant of time, you might need to make the decision, okay, I'm going to pull X% from the wind turbines, Y% from the solar panels, etc. So again, it's a big optimization process at the power grid level or at the power system level, you know. So in order to do that, you have to have good communication system so that you have a good read of the status of all the supplies and loads in the system. And at the end of the day, as I mentioned, you are just trying to optimize the load, the supply and demand at any instant of time. But again, the topic of smart grid is also a huge topic, you know. But at the center of it is control. So now, if we shift gears to traction and propulsion applications, and I'm gonna speed up a little bit because I know that I have like 10 minutes left or so. So I'm gonna start with some of the applications that are not very common, and then I'm gonna make my way to the more common ones and tell you what is happening there. You know, so mining applications is something that typically most people do not think about in terms of electrification. So mining has a lot of vehicles that are being used. So usually they are categorized as surface mining. So what you are seeing here to the left, these are like the large off-highway vehicles, and you can see these are like again, if any of us stand beside it, probably our heads is going to be at the center of a tire here. But these typically have diesel generators, diesel electric generators, and the generator is feeding four wheel motors. So each of these wheels have an induction motor embedded in them. That's how they are propelled, you know. The other one is underground. So usually in underground mines, there are all kinds of vehicles that are used for excavation, to remove material, to move people. So there is a big push, and I'm going to focus more on the underground mining. You know, these are typically historically are diesel electric vehicles, and there has been a big push to kind of electrify those and make them either pure electric or hybrid. The reason is, again, talking about the theme of harsh environments, and also extracting sources of energy becoming more difficult, mines today are deeper than ever. I mean, I don't know the most recent number, but at least years ago, a country like South Africa, which is big in mining, had mines that go up to 10 kilometers underneath the surface of the earth. So you are talking about 6 miles. So obviously, you don't want. This is a huge risk for the people working in the mines. If they are operating diesel electric vehicles at that depth, and the quality of air that they would be working in is again is a big risk. That's why there is a big push to try to electrify this whole space, and also not only electrify it. I think the long-term vision for mines is to basically use also autonomous vehicles as much as possible, again in the direction of reducing the risk for workers. So you can imagine that there is a lot of, again, research and engineering development that's happening in that space. And also, if you add to it that all these vehicles, everything that operates in a mine has to adhere to strict regulations, especially being explosion proof. So again, a lot of engineering work that goes in that direction. Uh, High speed rail, this has been happening. I mean, maybe not here in the US or in North America, but in Europe, in Asia, there is the electrification of trains and having high speed train. This is an example of an Alstom AGV traction system. This is not new, but this is many years old now. But again, this use like 720 kilowatt and advanced PM machines to propel the train, and the train in total has around 20 megawatt of total traction power. So again, globally, maybe not in North America, but the electrification of rail transportation and trains is continues to be a big initiative. This is just very specialized, but people also are working on what is called maglev or magnetic levitation. Uh, I mean, there are few examples here and there, but the goal here is that if you really achieve that this will cut the travel time significantly. So I mean, if you go to Shanghai as one of the demos that you can take the train from downtown to the airport in like a few minutes. So people are also working on trying to achieve this magnetic levitation for propulsion systems, especially for like trains. Uh, Again, since time is short, I want you to be also aware that marine propulsion, a lot of electrified and more electric systems for marine propulsion are being developed for a broad range of applications, really, for yachts, for ferries, for supply ships. I'm not going to get into the nuts and bolts of what type of components are being used, but again, this is a big space, and both on the civil side of things, and also a lot of stuff on the defense side of things. So the Navy and stuff also have been working on electrification for a long period of time. Yeah, this is just shows you an example. This is uh, for people who work or know or familiar with electrical machines. This is kind of very unique. So this is uh, a high power PM motor. It's 18 megawatt, and yeah, many unique features in this thing. So this comes from a company called DRS Technologies. Actually, it happens to be local here in the Milwaukee area. Sorry, I don't know what happened here. Yeah. So sorry, I was having some difficulty here. Yeah, so again, in the remaining few minutes, I'm gonna try to hit some of the key things I wanted to bring to your attention. So electrification is not new to the aerospace industry. I mean, people have been working on the more electric aircraft, as I mentioned, for probably 3 decades or more. And the idea is, if you look at the level of loads and power required in a plane over the years. Now, in large commercial planes, you might be talking about 2 megawatt of electric power. So this is like, again, small power system that need to be managed on the planes, So this was the focus of the aerospace industry for years, But the big change that happened maybe in the last let's call it 10 years, 10 plus years, is that the level of emissions that's produced by the aerospace industry, as well as looking at fuel economy. Bottom line, now they are trying to do with planes what has been done with light duty vehicles. Basically, try to have hybrid and electric propulsion system. So, for what do we mean by hybrid and electric propulsion for a plane? First of all, these are like some examples of the planes that people have been working on for flight demos over the past few years. The idea of is that for hybrid, you are going to have still a turbojet engine, and then you are going to have a number of propellers that are driven by electric motors. So you can see here, these are examples of distributed propulsion. If you have a pure electric plane, then you don't have the engine at all. Basically, the whole propulsion is going to come from a bunch of electric motors driving propellers, Yeah, this comes from NASA, Glenn Research Center. Kind of the all electric system is shown here. So you are going to have some sort of batteries for energy storage, and this is going to be feeding a number of motors, and these motors are going to be driving propellers. For large commercial planes, you go with a hybrid system. If you try to go for pure electric, first of all, it's going to be very complicated to get certified by the FAA, for example, in the US, but also the weight of the batteries and everything becomes daunting, So one idea is that you funnel like 10-20% of the jet engine power through a generator, and this generator powers a number of motor that drive a number of propellers. So again, you are going to have the engine and a number of propellers, and there are all kinds of other system configurations. Again, the series, hybrid, parallel hybrid, etc., similar to what happens in vehicles, But this has been fascinating. I mean, I put this. I always put this slide because one of the very early companies that developed one of the best motors for this space was Siemens years ago now. And Siemens is actually was never an aerospace company, but that division of Siemens that developed that got bought by Rolls-Royce eventually. So the landscape changed quite a bit over the past 10 years, Visually, this is kind of shows you there is probably, I don't know the exact number, but globally, probably there is a couple hundred startups around these small planes, and there is like all kinds of various applications for air taxi, for package delivery, for delivering medical equipment, regional regional air mobility. So you are going to see in the news, probably you might recognize some of these names, but you can see how radical and how different some of these small planes are, For the sake of time, I mean, this is just kind of and a timeline of the various planes and the flight demos that were done over the years, and you can see that when it comes to the single aisle commercial planes, this is still a moving target. I mean, initially the goal to have a hybrid system for these planes was like 2030. This is still kind of open-ended, but there is a lot of global effort to make this happen. So big players like Airbus, Boeing, GE, Pratt and Whitney, Rolls-Royce, all these are involved in this effort over the past 10 years or so. Also, unmanned unmanned planes like drones, but big drones. There are big drones that can be used for inspection of compression lines, blades of wind turbines, various activities. So also that hybridization and electrification is going to deal with unmanned planes as well. Uh, I think I'm almost past time, but again, I'm gonna try to wrap up in just a few minutes. The interest in light duty vehicles continue, and I'll tell you briefly what are the drivers here. I mean, you always try to get lower cost, higher efficiency, but one big issue, especially now in today's political environment, is you hear about probably rare earth material. I mean, so basically, the majority of traction motors and generators that go into electric and hybrid vehicles have something called permanent magnets, and these permanent magnets have something called rare earth material. And I mean, the majority of these materials come from China, 90% or so. And when there is political tension, the price of these rare earth materials and the sustainability of the supply chain gets questioned. So a big effort that has been ongoing for the past 15 years or so is how to come up with motors and generators that have the required performance while eliminating rare earth materials. I'm not gonna dive into the nuts and bolts of that, but if you follow the news, this is became again a very hot topic these days. Uh, uh, just briefly also industrial applications, so motors that are used to drive in the various industrial applications, cooling fans, etc. This is kind of relate to the third definition of electrification, basically replacing legacy drives with variable speed drives. So you see now that many companies, WEG, Baldor, ABB, they offer variable speed drives that are based on permanent magnet machines that are more efficient than induction machines. So again, industrial applications also is a big area. A lot of motors are used in industrial applications. Again, I apologize that the time is short, but also there is something called linear machines. These are used for compressors, for refrigeration. They use for actuators in aerospace and other applications. Also used in water desalination. So again, a broad range of activities where electric systems are being considered. Uh, the new trends, in a nutshell, really, this space of electrical machines and power electronics is like anything else. It is fairly saturated. So really, to get a step change in performance, you have to make some new discoveries in terms of materials. So new materials is at the core of what we can do. So there is a lot of work going towards advanced magnetic materials, whether new magnets without rare earth material, high strength magnetic materials, etc. I'm gonna skip this. This is too detailed, but just keep in mind that materials is at the core of what we do. Insulation. This is what insulation system. That's always what fails in electrical machines. So because of the harsh environments, we need high temperature insulation systems, high thermal conductivity. So it's insulation systems so that we can extract heat easily out of the systems and cool them. Insulation systems for higher switching frequencies, partial discharge free insulation systems at high altitude, especially now for propulsion systems for aerospace. Higher system voltage are being considered. So again, I know I'm rushing through this, but just keep in mind that materials is at the core of this. On the power electronics side, the big change is something called wide band gap devices. You might have heard the term silicon carbide or gallium nitride. And also another big theme is how to have tight integration, like what's shown in this figure. In the past, the inverter would be like a box, and the motor would be like a cylinder, and they are far apart. Now there are all kinds of at the system level, there are all kinds of very smart ways to have them tightly integrated that saves space, cost, and also EMI issues. When you have long connections and stuff, you start running running into electromagnetic interference issues, So in conclusion, I mean that energy sustainability space is truly multidisciplinary. It's kind of generating a lot of work for people like myself, and yeah, it's a good time to be in this area. Again, I apologize for rushing a little bit, and thank you for your attention, and would be happy to take any questions you might have.
Thank you very much, Ayman. That was really an interesting talk. So we have a few questions in the chat box. So I'll just go through them and you can answer
Sure.
the questions. So the first question that we have is basically a combination of three questions. So is really e-mobility a solution is the first question. And then how is the battery disposal can be a solution or a problem? That is the second. And the third one is what are the mechanisms to deal with it?
I mean, whether e-mobility is the solution, I think so, and that's why, and that's not my personal opinion. If you see, again, I mean, I mean, I'm trying to kind of separate politics from that because unfortunately topics they're like renewables and EVs and stuff are politicized, especially here in the US. But if you look at purely from a technical and practical point of view, I mean, you see companies like GM and Ford pretty much said that the future is going to be EVs. That being said, even though today the number of EVs has been increasing significantly, but there are some big challenges there still. I mean, if you really want this to be a reality, the charging infrastructure need to be there, and I think that's kind of one of the work in progress areas. So I mean, without a proper charging infrastructure, that might not materialize. In terms of batteries are still the choke point for example, for light duty vehicles. The main, and that's why when you buy a hybrid or EV specifically, you get a special warranty for the battery, because I mean, if something happens to it, it's expensive, and that's why a lot of work used to go towards battery development. That's still the choke point of the system. How to dispose of batteries is, I don't think it's a fully answered question, but it fits in the bigger context of what is the circular economy of electrification. Because if you think about it, uh, it's not only the battery that's challenging, what to get rid of it, but everything I talked about here involves using much more electronics and power electronics for all these applications. So a question is, what do you do with all these electronics at end of life? Today, if you look at how this gets disposed of, it's awful. I mean, the majority of it gets sent to countries in Africa, and you can see even videos about that on YouTube. And this gets burnt in a very, very crude way, and poor people are just who are not equipped with anything, inhale all what comes out of this, what comes out of this process. So the answer I'm giving a long answer, that what is the full life cycle of these systems, and how to dispose of batteries, electronics, motors, how can you recycle some of that. I think that's still an open-end topic, that's still work in progress. I don't think there is a clear answer for that, especially now. Maybe with the number of EVs and stuff, that's manageable. But if we envision a future where the majority of vehicles become electrical, then this is definitely an issue that has to be addressed.
Mhm. Okay. Okay. So the next question again is from Amanda. So the question is, how is the wind energy industry tackling the issue of bird deaths? So this is an
Sorry, of what?
interesting, the death of the birds because of this windmills. So
So
how the wind energy, yeah.
So, so, I mean, I don't want to be, yeah, I mean, I'm just going to refer to books and references. I mean, I think this is one of the not very accurate perceptions about wind turbines. I mean, if you look at statistics of bird death globally, uh, you find that birds that die due to wind turbines is much much lower, for example, than just birds really crashing into buildings and windows of buildings and light posts and stuff like that, you know. I mean, I on top of my head, I can probably mention a couple of references, but if you look at studies about the environmental impact of wind turbine, the numbers does not support the perception that wind turbines cause significant bird death.
Yeah, that's true. Um, then the third question is also from Amanda, but I'll come back to this little later. I'll take the next question from Fengwan. So he's asking, my understanding is that it would be better to have many local energy sources so that the energy needs can be met locally. So how do you comment on this?
Yeah, I mean, I one vision for that distributed generation. I mean that concept of microgrids. So yes, that's true. Ideally, you would have the system composed of a number of microgrids, and each microgrid kind of is responsible for a local zone, and these microgrids can operate in either islanded fashion, so it's not connected to the main grid if it is self-sufficient, or in case it needs more power or have extra power to sell, then it can be connected to the main grid. So that's true. A lot of research is going toward that microgrid concept, which basically tackles the supply and demand at a more local level, you know.
Yeah, okay. So I can see a comment from Charlie, which is apparently an answer to the previous question related to the bird death. So he also is saying that in USA, house cats kill more birds than the wind turbines. So yeah, this is in the line of what you answered. So there are many other probably reasons which is responsible for bird deaths other than the wind turbines. But he also has a couple of questions. What is the most disruptive technology that you talked about? Which technology is hard to predict where it will go?
I think the aerospace electrification. That's the biggest one because again there is a lot of interest. As I mentioned, there is a large number of startups for various applications, and it's gonna be and aerospace is typically a fairly conservative industry. To get anything to go on a plane, that's usually goes through a very rigorous process and certification and stuff. And just visually, if you look at the smaller planes and the concept of having electrical motors and stuff propelling planes, that's very very disruptive. So that's why in the next few years it's going to be very interesting to see what happens with the certification, how many of these companies survive, whether the big players are going to really follow through with having hybrid planes. Again, the Airbuses and the Boeings of the world, where this goes, I think by far that's the most disruptive space, you know.
Mhm. So I just have a very small follow-up question. So it's a query basically. So is there any full, I mean, all electric aircraft currently in civil aviation available, or is
No,
there anything
no,
hybrid?
no, nothing. I mean, there are some small planes that got approvals for like short flight demos, but no, there is nothing that's certified and fully electric today. No.
I see. But they also use something hybrid as of now, or currently it's
Even even the even
no.
the hybrid, nothing is officially certified and in production yet. So so
Mhm.
so so still work in progress, you know. I mean, I think some companies like Magni X and couple more Joby also are close to getting certification, but no, nothing. And another, I mean, maybe I should make that comment. You know, another big challenge for that space is the supply chain for these electric components. These do not exist today. So most of the companies use as close, like off-the-shelf components or mildly customized components. But if this space really takes off, then a whole network of supply chain is gonna be needs to be established to provide all these electrical components that don't exist today.
I see. I see. Okay. So Charlie has another question, which is interesting. So his question is, what other technologies should an electrical engineer learn? Mechanical, chemical, or biomedical? What is your comment on that?
I think I think in the context of what I'm talking about, mechanical, definitely. Even like I tell the students, the PhD students that I supervise, that the days of one being like just focused on one area of engineering are long gone. So probably as an
Mm.
electrical engineer, you need to have some proficiency in thermal analysis, stress analysis, have some level of understanding of materials. For example, one area that's coming in, like I talked about materials, but I should have also mentioned something like additive manufacturing. That's now is opening up the design space in very interesting ways. So I would say, yeah, maybe mechanical for an electrical engineer, especially working on machines and power electronics. Yeah, you
Mhm.
have to have some thermal, mechanical, material knowledge. I
Yeah.
mean, you don't need to be an expert, but at least know, uh,
Uh-huh.
have some working knowledge about these topics.
I see. I see. So I'm again coming back to the third question of Amanda. So she asked, considering the example of the flower form of the solar system,
Yes.
how is biomimesis considered to create more equipments, not just in solar panels, but the other solutions?
Sorry, can you repeat that? I missed the part after the solar flower. What did you say?
So it was considering the example of the flower form of the
Yes.
solar system. How
Yes.
is biomimesis considered to create more equipments, not just in the
How,
solar panel, but in other solutions?
sorry, I missed the word again. How is what?
Biomimesis. Maybe what she wants to know is how a similar structure can also help in developing new technologies, just not in the solar panels, but other technologies as well.
Not sure
Maybe you
how.
want.
I'm not sure honestly how to answer.
I think what she wanted to meant is biomimetic, if I'm not wrong. So how we can mimic something which is there in the nature to
Yeah,
get
yes, I got
more
what you're
efficient.
saying. Yeah.
Yeah.
Yeah, I mean, for example, there is one example. People are very creative. So there is one example for wind. There is something that looks like a tree that you put in beside the building, and the equivalent of the leaves are small, like they rotate. Basically, they spin when they are exposed to wind, and each one has kind of generates electricity. So this is another idea similar to that solar flower. There is a wind tree basically, and I have seen a couple more examples. But so people are trying, yes, to try to mimic some of the stuff that exists in nature. But just to be also realistic about things, these are very interesting ideas. But solar specifically is still not cost effective at the residential and commercial level. If you look at the levelized cost of energy, there is still work to be done to make that competitive. And that's why in many states, this is subsidized if you install solar panels on your roof. But where solar specifically is shines in terms of its levelized cost of energy is at the utility scale, meaning if you want to go build a solar farm that produces tens of megawatts, that's very cost effective today. But at the residential level, still. But again, people are looking at all kinds of ideas. The two I am aware of that comes to mind is that solar flower. And again, if someone is interested, I can send them the link for this wind tree. But but yeah, that's the extent of what I know right now.
I see. Yeah. That would be helpful if you can send the links to
Sure.
the participants. Yeah, so with this, the question and answer session is now over. And I would like to thank you again, Ayman, for this interesting talk and this question and answer session.